Hey everybody, welcome to Lab 4. Let's get right into it. Okay guys, so here's a brief run through of my Arduino code. Initially I set up my two input pins for both the potentiometer and the end scope output frequencies. Obviously I set my baud rate to what's needed for VSA. And then in my void loop, I read those two pins, and what I actually did here is set up something a little bit for my sanity. I created another integer that could basically switch me to the necessary frequencies for the lab a little bit easier rather than having to try and dial them in manually every single time. So you can see the if statements there to do that. And of course then I send the signal out to the serial monitor for VSA, and to set up or emulate the sample frequency, I built a delay here. All right guys, so here's a breakdown of the outputs from VSA with the time graphs and then the frequency domain plots. This is just that test function kind of proving that everything works, and now I'll run through everything for you. Here is the input frequency of 75, running down the sampling frequencies from 500 all the way down to 100. Now we're going to the input frequency of 100 and continuing in the same pattern. This is now input frequency of 215, and you can see that now we're seeing a lot more aliasing in our frequency domain charts. Input frequency of 300, and pretty much all my values here had aliasing. Alright guys, so here's my table of values. I only did one example using a folding diagram. Actually I did two, because one of them had aliasing and one didn't. You could see we break down to get our Nyquist frequency and then put things in a ratio of the Fin to Nyquist, and do our folding plots to get down to our aliasing frequency. That one turned out to have no aliasing, but then I did another one here, and you'll see that pretty much I realized that remainder there, if you keep it in decimals, gives you the ratio you're going to use for your aliasing frequency. So here's the summary table, guys. One more time. I'm just going to run you through what we have going on here. Most of my sampling rates were pretty close, except at the high end. I think that's a combination of the lack of a full 5 volts and then the fact that I used delay microseconds rather than the millis command. The delay and sampling rate there is a pretty easy calculation for DT that you can see over there. Nyquist frequency is just half of our sampling frequency, and then you can see the outputs we have here. And you can basically see as the sampling, well, it's a combination. You can see as the input frequency goes up and the sampling frequency goes down, kind of in a cross pattern here, we get more aliasing, and that's pretty understandable as we're getting less samples for more incoming information. All right, guys, on to exercise 2. I thought I'd just take a minute here and give you a basic view of the setup here, although it's not very complicated. So what I'm really seeing here as a big difference between the square wave and the triangle wave is that the square wave gives far more harmonics than the triangle wave. And this makes sense because a triangle wave is more similar to a natural sine wave. And as we discussed in class, you know, there is no such thing as an actual square wave. If you really zoom in close enough, you're going to see these oscillations in something like a sine frequency just coming together to form something like a square wave. And that square wave then obviously is going to have a lot more aliasing in these frequency domain charts.